Alrighty. Can everyone see the presentation?
Yes, it's good.
Excellent. So hello everyone, I'm Mollie Schwartz. I'm the technical lead for MIT Lincoln Laboratories collaborative work on the Advanced Quantum Testbed program. And I'm really excited to be here today to tell you a little bit more about what we're doing in this program. So Lincoln Lab has three broad goals in the Quantum Testbed program. First, we're designing, fabricating, validating, and delivering testbed devices of our own design. In particular, the inset on the left here is our 5-qubit processor that we're going to talk a little bit more about later. Second is 3D integration of our own designs, and as Roger mentioned, and we'll talk about as well, designs that are generated at Lawrence Berkeley National Laboratory, fabricated and packaged at MIT, and then sent back for integration into the Advanced Quantum Testbed facility, as well as development of novel and particularly 3D integrated circuit primitives that are going to allow us to make our devices higher coherence, higher fidelity gates, and overall better performing. So starting with a little bit of an overview of Lincoln Laboratories' history in the superconducting platform area. We have a long history with some, a smattering of references given at the bottom here in the superconducting qubit world, including well-vetted qubit designs and layouts, increasingly a robust and sophisticated control and benchmarking suite that allows us to tune up single and 2-qubit gates with high fidelity and most importantly, with repeatability. And we validate our circuits and our control software against NISQ algorithms of near-term interest. And in particular, on the bottom right, we've recently demonstrated a control Z entangling gate fidelity of 99% fidelity. In addition to the underlying superconducting qubit technology, we have a sophisticated suite of 3D integration and packaging capabilities, including superconducting air bridge crossovers, flip chip bump bonding that allows us to do off-chip qubit control and readout, superconducting through silicon vias that open up a wide variety of new capabilities for 3D integration, and packaging solutions, including a full-time staffed packaging laboratory that's compatible with the 3D integration template. Our mode of interacting with the community at large has historically been in the form of papers and traveling wave parabolic amplifiers going out from Lincoln Laboratory and learning a lot about advances in materials and devices and gates coming in from the superconducting research community. But what's been really exciting about the last several years, and the AQT is certainly an example of this, is that we're entering a new stage of collaboration with the community at large, where not just research products and amplifiers are going outwards, but increasingly validated quantum processors, design tools are being delivered directly into testbed facilities like the AQT, also including a few IARPA testbed facilities. Circuit designs are coming in from external collaborators being produced and turned around to go into those facilities. And this enables us to interact with the broader research community in a way that goes far beyond what we've been able to do before. So we can take in and provide custom designs, custom circuits that may be targeted to a particular application, interesting to a particular set of researchers, and in this way help move the field forward by leveraging our measurement and fabrication expertise. Particularly for the Advanced Quantum Testbed facility, as I mentioned a few slides ago, our Generation 1 Lincoln Laboratory device is shown on the left, is a 5x1 chain of Transmon qubits. They're capacitively coupled to one another in an always-on format, which enables us to do very fast 2-qubit gates. This device was fully characterized at Lincoln Laboratory over the last few months. It has single qubit gates in excess of 99% fidelity, 2-qubit gates on the order of 98% fidelity, and this device is actually being packaged for delivery to the AQT within the next few weeks. So we're very excited about that. Also in 2020, we're expecting to deliver our second generation of devices, and these are going to include 7 to 9 qubit chains, which will allow us to access more complicated and larger problems, for example, in verification and validation, in variational quantum eigensolvers, et cetera. And we're also interested in exploring devices that have slightly higher connectivity. So rather than a linear chain of qubits, a 2x3, a 2x4 qubit array. And so this allows us to explore the interplay between increased connectivity, which in principle will allow us to generate entanglement across the chip significantly more efficiently. On the other hand, it leads to additional always-on couplings. It leads to potential issues to explore with frequency crowding. So the trade-offs between increased connectivity and increased complexity are something that's really interesting to us and to the community at large. I show here a planar implementation of the chip. Our generation 2 devices will be fabricated with both planar and 3D integrated iterations. And we're going to talk a little bit more about what that looks like. In parallel, we're working on new circuit primitives that are going to allow us to reduce coherent errors in the system. In particular, I'm showing here a tunable coupler that was proposed by our colleagues on MIT campus and is currently being tested there. And this is a novel approach for knowing of the always-on capacitive couplings between neighboring qubits. And the general idea is to put an extra spare qubit in between the two target qubits, tune the frequency of that second qubit to an operating point where when the coupler is idling in the off position, the residual coupling between qubits 1 and 2 is nulled. When the coupler is turned on, we can have significant coupling between qubits 1 and 2 that's sufficient to do fast and high fidelity entangling gates. And so this and other devices like it are going to enable us to do high fidelity gates, but also to null these always on coupling terms that can create issues for longer and more complicated algorithm implementation because we're reducing the coherent errors. So these couplers and others like it will feed into future AQT designs. So next, I'd like to talk a little bit about 3D integration. I won't belabor this too much because Roger gave a really great introduction to why we want to do 3D integration and why it's important. So we're going to talk about 3 layers of 3D integration that are under development at Lincoln Laboratory. Air bridge crossovers, flip chip integration, and then we're going to talk a little bit about high aspect ratio through silicon vias and what those enable. So starting with what I call 2D plus, which is air bridge crossovers. It's 2D plus because these are fabricated on a single chip like a planar device, but because it allows us to bridge between different components on the chip, it really is a first foray into 3D integration. So the most simple thing that one can do with an air bridge crossover is to connect different versions of a ground plane. So this is sort of a passive use of an air bridge crossover. This is already extremely important for devices like those that are being integrated into the AQT, because better connections between ground planes will allow us to reduce flux crosstalk from on the order of 40% from qubit to qubit to on the order of 5%. And 40% is really a game stopper when it comes to being able to address qubits individually. The next most sophisticated thing one can do with an air bridge crossover is use it to actually route active signals over one another. So in the middle, what you're seeing here is a readout line that's being crossed by a qubit flux bias and by a microwave bias. And we're able to use air bridge crossovers in a flux bias line because these are superconducting crossovers. It's a full superconducting connection between the two sides. So this allows us to do quasi-3D routing of signals without having to introduce a full new plane of a chip. And then the next most sophisticated thing one can do with an air bridge crossover, particularly our crossovers because they're fully superconducting, is to actually integrate them into the qubit loop itself, basically connecting Josephson junctions via a superconducting crossover. And this can be extremely useful, particularly for applications in which you need a very strong mutual inductance between two elements. You can actually have 2 qubit loops intersecting and lying directly on top of one another, which allows you to get very strong coupling between nearest neighbor qubits. So air bridge crossovers is a technology that we're very familiar with that enables new and improved circuit primitives and qubit designs. And this is already deployed in the AQT devices that are being delivered. The next level of sophistication, as Roger gave a good introduction to, is flip chip integration, where now either to the qubit chip or to an interposer chip, we add indium bump bonds, and we use those indium bump bonds to mechanically and galvanically connect 2 chips. And so we have a great deal of experience with flip chip integration at MIT Lincoln Laboratory. Here I'm showing some data from a 5-qubit flip chip device that's currently under test. We have moderate T1s of around 20 to 30 microseconds, T2 echo roughly double that. This enables us to demonstrate single qubit gate fidelities very close to 99.9%. And we are currently tuning up 2-qubit gate fidelities that we expect to be of comparable performance to our planar equivalents. So we are demonstrating off-chip qubit control and readout in the flip chip architecture. And this capability is going to be deployed in the next generation of AQT devices that we design and deliver. As Roger mentioned, a really great part of our collaboration with the AQT program is a design and fabrication collaboration with the team at UC Berkeley. So we have been working particularly with Roger for the past several months to port the design of the SpiderNet 8 chip into the Lincoln Laboratory process so that it is compatible with our particular 3D integration platform. So the device design and the testing is going to be led by the Berkeley team. Fabrication, 3D integration, and packaging will be performed here at Lincoln Laboratory. We're excited to say that the first set of devices in this design and fabrication collaboration is now entering fabrication. So we're really excited to see how those devices perform. Moving beyond into sort of the next generation of 3D integration, I want to talk a little bit about superconducting through silicon vias. At Lincoln Laboratory, we've spent a lot of time and effort over the past several years, particularly with the assistance of IARPA through the QEO program, developing high aspect ratio, high critical current superconducting through silicon vias. So what we're showing in the middle here is a cross section of a TSV. They're about 200 microns deep. They're 10 to 20 microns wide in footprint at the top and bottom of the chip. And the importance of this high aspect ratio is that the through silicon via is a small fraction of the size of the qubit itself, which means that we can use these TSVs to pass microwave and currents to control the qubits and read them out without adding significantly to the per qubit footprint on the chip. They're also, of course, useful for efficiently suppressing chip modes, which enables us to use larger and larger chips. And as a result, they're critical for high density and many qubit applications. And so to give you an example use case of what a TSV can buy for you in terms of design innovation, I want to do a little bit of a deep dive into the standard readout resonator, which is shown on the right here. It's this long meander line that terminates in this plus, which is itself the qubit. This is a fairly standard approach to reading out qubits. And as you can see from the length bars shown here, a standard readout resonator occupies 3 to 5 times more space on chip than the qubit does itself. So even from the start, it's adding substantially to the per qubit footprint. It also is limiting the qubit layout and connectivity because it occupies an entire side of the qubit. What we're developing is a compact lumped element TSV-enabled resonator, which is comprised of a spiral inductor on the bottom of the interposer chip that's connected to the qubit via the capacitance of a TSV that passes through the interposer chip and sits basically right underneath the qubit itself. And as I'm showing on the zoom in here, the size of these lumped element resonators is comparable to, and typically actually even smaller than, the size of the qubit itself. So the TSV integrated resonator allows us to do vertical readout integration. So now the qubit is sitting directly on top of the readout element rather than being lateral to it. And it allows us to do readout at a pitch that's equal to that of the qubits, which will enable us to do more densely packed quantum processors. So we have some really great results with these compact resonators. On the left, we measure about 400,000 internal quality factor at the single photon level that's relevant for readout applications. So it's a very high quality factor of a resonator, despite the fact that the TSV, the process of developing TSVs, adds significantly to the fabrication that the circuit undergoes. We can also do very high fidelity single shot readout, which is shown in the center here. We have a separation fidelity of about 99.7% in 2 microseconds of integration. And most importantly, it's compatible with long lifetime qubits. So we measure a typical T1 of about 40 microseconds for a qubit that's coupled vertically underneath one of these resonators. So we're very excited about this particular use case of a TSV for enabling a fundamentally new circuit primitive that has good capabilities for improving the scalability of our platform. And we're also developing other circuit primitives that similarly take advantage of TSVs to demonstrate performance improvements. So just to summarize the Lincoln Laboratory role in the AQT, we're fabricating and validating high-performance multi-qubit devices that will be integrated into the testbed facility and available to the user base. We're deploying advanced 3D integration capabilities to enable us to make larger and more complex qubit arrays. And we're developing novel circuit elements, tuners, readout resonators, control lines to improve both planar and 3D integrated circuit performance and scalability. Of course, it requires a very large team to do this kind of work. So I'd like to acknowledge particularly the folks whose names are highlighted in red, both at MIT Lincoln Laboratory and in the EQUIS team at MIT. And also the Microelectronics laboratory that does really wonderful work fabricating TUPAs, and in particular developing the TSV process. And so with that, I will conclude. I think we're going to do questions and comments at the end. But if you'd like to reach out to me, please shoot me an email at this address.
Thank you, Mollie. We will move to the last short talk in this 1 hour segment before we go into questions. That'll be Anastasia Butko.